In this video, I discuss why we use log-log plots in fluid mechanics when we have an experiment and we are trying to establish whether the data that we measure follows in power law. So what do we learn from a log-log plot? Now assume that we are doing an experiment. So for example, we're doing a wind tunnel experiment where we're measuring the drag as a function of the velocity. And we can set the velocity in our wind tunnel. So we're plotting a drag as a function of the velocity, but we non-dimensionalized everything. So what we are plotting is our drag coefficient as a function of our Reynolds number, which is a measure of the velocity. And our experimental data is not perfect, but it's going to look something like that. Well, maybe the data looks, we have different data points. And if we are plotting everything in linear scale, it's very difficult to see whether we have a power law. Now, what is a power law? That is simply when our drag coefficient would depend on the Reynolds number, like a Reynolds number to a certain power. This here is a power law. And what is of particular interest is the value of the exponent. So if we are plotting our data in a linear scale, then we cannot deduce easily the exponent, and we cannot see if the data follows an exponential, a power law. But if we plot everything in log-log plot, it's much easier. So what do I mean? So here we have y equals to CD, and our x is our Reynolds number. So if our data follows a power law, then y scales with x to the alpha. This is, if we plot this, we're plotting a linear plot. Now what happens if we are plotting, if we're taking the log of each side? So I'm taking the log of that scaling law. So I'm going to take the log on each side. So on the left hand side, we now have the log of y, and on the right hand side, we have the log of x to the power alpha. But you know that the log of x to the power alpha is actually equal to alpha times the log of x. So we see here that if y is a power law in x, then the log of y is going to be a linear function of the log of x. And so if we plot, instead of the log of y, if you're plotting the log of y, we call that capital Y, as a function of the log of x, which we'll call capital X, we see that the log of y is a linear function of the log of x, and that alpha is really the slope of that linear function. So if you're plotting things if your data satisfies a power law, then when you're plotting it in log-log, you know that your plot should be a straight line, and you can directly read the exponent from the slope of this line. Now let's see how this looks like. So let's take a simple MATLAB script. And so here I'm plotting different functions. And let's say that this is of course not experimental data. I wrote the function, but let's say that these four here would be experimental data. Okay, so you see in the four cases, I have data on the y, which I measure, which is decreasing with what I'm imposing, which would be u. So each function here is decreasing with u. It looks like all of these functions are going to 0, but if you're just looking at them, it's very hard to determine whether any of these are power laws. Okay, so let's see what happens when we plot these in a log-log. So here is the first example. I'm plotting this function, and here I'm plotting the data in linear scale. So I'm plotting, all of my data is limited between 1 and 4. That's just for the purpose of it. But you see that I have a decreasing function. Now, this is in linear scale. What happens when we plot the same data in log-log? Then we have this function. So first notice how you read a log-log plot. Now, I'm no longer reading the linear scale here, but I'm I have everything in log scale, so every increment of 1 or every equal increment is actually if you increase everything by a factor of 10. So this is 0.1, this is 1, this is 10, same here, 0.01, 0.1, 1, 10. This is the same data which I'm plotting in LogLog. Note that here my x value is limited between 1 and 4. That's what you have here too. In the x you go between 10 to the power 0, which is 1. That here would be 2, 3, 4. So I'm stopping here at 4. So it's between 1 and 4. And the data went between 0.4 and something which is on the order of 0.02, let's say. And that's what we have here as well. If we're reading this, this is 0.01, 0.02, 0.02, 3, sorry, 0.4. So this is between 0.4 and this point here, which is at about 0.02. So it's the same data. And what you can see when you're plotting it in LogLog is that this here is not a straight line. So you know that that here is not a power law. Now let's take another example. Now I have this function. It looks in linear scale quite similar. Right? So what happens if we now plot it in LogLog? So when we plot the same data, so this data in LogLog, now it is a straight line. So what we learn is that this is a power law. If you have a straight line in the LogLog plot, you have a power law. But you can also learn, remember, the exponent. The exponent corresponds to what we saw here. The exponent is now in LogLog the slope of your curve. So what's the slope of this line? So in LogLog here, you see when you're going from an increment of 1, you see that you need to decrease from an increment of 1. So this is a slope of -1 to have the same slope. Maybe it's easier to see if I'm going 2. So if I'm going here 2 decades up and I'm going 2 decades 1, then this line here has a slope of -1. And you see that this line, this slope is the same as the one in my data. So what you learn from a LogLog plot is that here you have a power law with an exponent -1. Now let's take another example. Again, when you see now, it's not easy to know whether this is a power law or not. So what we can do directly is plot in LogLog. When we plot in LogLog, we see that we have a straight line again. So we know that this is also a power law. And we can again read the exponent from the slope. And as you can see here, if I trace a line between this point and that point, then I have the right slope. Right? And that slope is a slope of, you need to go 2 decades to the right and 3 decades down. So that means that this is a slope of -3/2, so -1.5. So the LogLog plot allows you to determine that this is a power law and that the exponent is -3/2. Now let's take a last example. If I'm taking this example here, is that a power law or not? If that was my experimental data, would that be a power law or not? Now then we just need to plot this in LogLog. We see that in LogLog, this is not a straight line, and therefore we know that that here is not a power law. So you're using LogLog plots to determine whether, if you're trying to find a scaling relationship, for example, whether you have a power law, and from the slope in your LogLog plot, you can deduce the exponent of your power law.